Okay, good. As always, I'll be recording this class so that if you miss part of it or you want to go back later and watch me go through part of it again, you will be more than all right. So like I was just saying, all of the notes that we go over in class, including the ones even from the first week or for the first day, excuse me, are posted here on the Google Classroom. And you can find them by looking at the day that we went over them. So today is Thursday, March 4th. And so we can go to the Thursday, March 4th notes, which are about the laws of motion. So I really like starting out with the laws of motion when we kind of start talking about physics and movement. Not only because they're kind of the basics, they're the building blocks, but there also is stuff that makes a lot of sense if you just kind of think about it, but is put into a more kind of scientific way. So a lot of this stuff you're probably a little bit familiar with already, even though you may not even realize it yet. So these laws of motion are also oftentimes called Newton's laws or Newton's laws of motion, named after Isaac Newton, a physicist and mathematician who lived in, I want to say it was like the late 1500s or mid 1600s, so a couple hundred years ago. Isaac Newton is an extremely interesting guy. He's widely considered by scientists to be one of, or if not the smartest person who ever lived. Not only did he determine these laws of motion, he also developed the initial idea of the law of gravity, so why exactly things fall down to the earth. You may have heard the famous story that he was like sitting underneath an apple tree and then an apple fell out and hit him on the head. And instead of being mad because he got hit on the head by a tree, he started thinking about why the apple fell down to the ground, and that led him on the track to describing gravity. Whether or not that story is true and actually happened, scientists are kind of mixed about it. Nobody really knows for sure. But he was an extremely intelligent and smart guy. He also created an entirely new type of math called calculus in order to help him with some of the equations that he was working on. So extremely smart dude, and especially famous when it comes to physics for these laws of motion, the kind of basic principles for how different things move. So there are three laws of motion, the three that we are going to do today. There's the law of inertia, there's the force equation, and there's a law of action reaction. So a lot of these probably won't make sense to you yet, but hopefully by the end of today, everything on this slide right here will make a little bit of sense. So we're going to go through these one by one individually, but the basics, just to kind of lead it off. The first law says that something at rest will stay at rest, and something that's moving will continue moving until some sort of outside force acts on it. The second law is an equation that describes force. It says force equals mass times acceleration. And the third law says that for every action on an object, there is an equal and opposite reaction back on the initial object. So we'll go through each one of these laws one at a time, and I'll kind of break them down for you and explain how exactly they work and what they mean. There's a lot of kind of sciencey jargon in here, but what they're actually talking about is a lot of fairly simple ideas. So Newton's first law, the first law of motion, also sometimes called the law of inertia, which we'll talk about in a minute. An object at rest will stay at rest rest is just a fancy physics way of saying like still or not moving. So an object that's not moving will keep not moving, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force or an outside force. Like I said, kind of a lot of physicsy, sciencey words and jargon in there. Basically, what this even means is that an object is going to keep doing what it was doing in the same direction and speed unless acted upon by some new, different, unbalanced force. So the first part of the first law, the part about an object at rest will stay at rest, means that if an object is sitting still, it'll remain stationary. It's not going to move until some other force comes and acts on it. So like my water bottle that I have here, if I put my water bottle down on the ground in front of me, hold on, let me put it down right there. So if I put my water bottle down here and then stop touching it, my water bottle is not going to move, right? It's going to stay there and it's going to keep sitting here until something comes along and moves it, puts a force on it. But if nothing does that, then this water bottle will keep sitting on this table forever and ever and ever. If there's no other force that comes along, the water bottle will not move. It cannot move. It'll stay still. All right, on the flip side, if something is moving at a certain speed, until some other force acts on it, it'll keep moving at that speed. Right? If your car is going at a certain speed down the highway, if you want it to go any faster, you've got to push on the gas a little bit, which provides acceleration to the wheels and spins them faster, right? If you don't do that, then the velocity of your car won't change. So it takes force in order to change the motion of an object. And force is just kind of a fancy science way of saying a push or a pull of some kind. So we'll talk about different types of forces and what exactly force is at the beginning of, or at the end of the week next week. But for now, just know it's some sort of action, some sort of movement. So if you don't do anything to something standing still, it's going to keep standing still. If you don't do anything to something that is moving, it'll keep moving at that same speed and direction. So there needs to be some sort of outside force to come in and change the speed or the direction. So when I say unbalanced force, instead of just saying force, right? So I could just say, oh, this water bottle will stay still unless a force acts on it. I can't say that because there are already forces acting on it. It's just that those forces are balanced. So when you lay something down on the table and set it still, like a water or like a physics textbook, there are a couple different forces that are acting on it. Yes, Nancy, these notes are currently posted on the Google Classroom, and they're posted there for you guys as well. Oops. So if you go to the Google Classroom in week 1, which is where we're at right now, the Thursday notes are there for you guys to look at, and they'll be there until the end of the class. So you're free to go back and look at them anytime.
Okay, thank you, because I like to print them out in case so I can go back.
Yep, you're free to print them out as much as you want.
Thanks.
All right, so like I was saying, the reason I was saying unbalanced force earlier, instead of just saying force, is that there's already forces acting on these objects. If you're on Earth, that means that you're always going to have the force of gravity pulling you down, right? This is what keeps you down on the ground, down on the floor. This is why when I lift my pen up in the air and then drop it, it falls down. So gravity is always a force that is on our objects. When I move something like a pen or my water bottle onto the table, the reason why it doesn't go down to the ground is that the table is pushing back up on the book or on my water. So these forces are balanced. The force of the table holding the book up is equal to the force of gravity pulling the book down. So we have balanced forces, which is why the book or my water bottle doesn't move. It stays still. It stays at rest, as we say in physics. So this is a balanced force. And when we have balanced forces, that means that we don't have any change. We're not speeding up, we're not slowing down. Or in the case of a book or a water bottle on a table, we're not moving. So if those forces are balanced, then there is no change in motion, or staying the same way that we were before. Right? The first law is all about things staying the same. Either things are going to stay stopped, not moving, or things will keep moving the exact same way until some unbalanced force comes and acts on them. Only if and when we have that unbalanced force is our speed or our direction going to change. All right, so you also sometimes see the first law referred to as the law of inertia. So inertia might be something that you have heard before and kind of know what it means, but kind of not really also. It essentially is just a word that describes the tendency of an object to resist changes in its motion. So the first law is just saying that objects are going to resist a change in motion, and it requires force in order to get them to change how they are moving. The thing about inertia that we haven't really talked about yet is that inertia depends on mass, which is essentially the weight of something on Earth. So the more mass that an object has, the more inertia it has, so the harder it is to change its motion. Right? Really, really heavy things, it's hard to get them to move or get them to change direction or to get them to stop compared to things that are smaller or lighter. So the law of inertia is basically the same as the first law. It just says that things tend to stay still or keep moving in the same way until some other force acts on them. And it also brings in the idea that the more mass that something has, the more force you're going to need in order to change that movement. So for example, if we have these two buckets here on a string, one is just an empty bucket, but the other one is filled with sand. So sand is pretty dense, it's pretty heavy. So this is a heavy bucket right here, a lot more mass in the sand bucket. So right now they are both at rest, both sitting still on these ropes. So that means that it's going to require some sort of force in order to get them to move, right? Right now, the force of gravity pulling the buckets down is being balanced, not because there's a table under them, but because there's this rope attaching them to the top of this pole right here. So the force of the rope pulling them up is balanced by the force of gravity pulling them down, so they stay at rest. They stay still. If we want to get them to move, then we're going to have to apply some sort of force ourselves. What inertia says is that it's going to be easier for us to get this bucket to start moving than this bucket. All right, it's easier to change the motion of an object with a small mass, like this guy, versus the motion of an object with a large mass, like this guy. It's harder to push this one and get it to start swinging than it is to push this one. Again, something that you probably understood already, but now we're just kind of putting these science physics words to it. So heavier objects have more inertia, so they're harder to move. Same thing with if you have like a person running at you for like a football tackle or something versus an elephant running at you. An elephant has a lot more mass than a person. An elephant is usually a couple thousand pounds at least. So that elephant has a lot more inertia than this little guy does down here. So if somebody's charging at you, it might be fairly easy for you to push them to the side or push them out of the way, push them down on the ground. Elephant, that's going to be a little bit more challenging. Not quite as easy. Because more mass of the elephant means that it has more inertia. Not only is it harder to get it to slow down and stop, but also it's harder to get it to just change direction. So if you want it to keep going the same speed, but maybe go just to the side of you and not right over you, it's really hard to change that direction of that elephant. And that's all because the law of inertia says that things with more mass are harder to change the motion. So essentially, if something has a large inertia because it has a large mass, that means that if something is at rest, it'll be hard to get it to start moving. If something is moving already, it'll be hard to get it to slow down or speed up. And if something is moving, it'll be hard to make it change direction, right? Imagine if you have like a dodgeball and a bowling ball rolling at you. It'll probably be easier to kick the dodgeball and move it out of the way than it will to kick the bowling ball and get it to move out of the way. Because the bowling ball has a lot more inertia. It's going to resist you kicking it and probably make you hurt your toe. All because it has a larger mass. And the first law says that things that are in motion are going to stay in motion until some new force moves them. Which means that if it has a large inertia, it's going to take a big force in order to get it to move. So inertia, like we're just saying, means that things that are in motion want to stay in motion. So they aren't going to slow down unless something causes them, some outside unbalanced force causes them to slow down or stop. So if you take the example of this poor guy in the sports car here, he is dumb and he did not put his seatbelt on. So while he's driving in his sports car at 80 kilometers an hour, his sports car hits this brick wall right here. And the brick wall puts a big force on the sports car and causes it to come to a stop almost immediately. So it goes from 80 kilometers an hour to 0 kilometers an hour pretty quick. This man right here is not wearing his seatbelt and is driving in a convertible, so he does not have any sort of roof above him. Initially, he is also traveling at 80 kilometers an hour in his sports car. The sports car stops, but the man does not stop. He still wants to keep going at 80 kilometers an hour because the first law of motion says that things that are in motion can't be changed unless some other force acts on them. So he's in motion right now, and since only the sports car got hit with the wall, since he doesn't have a seatbelt on, he doesn't have any unbalanced force acting on him, so he's going to keep traveling forward at 80 kilometers an hour until a combination of gravity and the pavement put enough force on his body and his face in order to get him to slow down and stop. So that is why seatbelts are so important. Having that seatbelt across your chest means that when your car hits something that causes it to change its motion very quickly, that seatbelt will act as the force that causes you to slow down and change your motion as well. So people get flung out of their cars all the time in traffic accidents when they're not wearing their seatbelts because the car hits something and comes to the stop, but you don't hit anything. And the first law of motion says that you're going to keep moving until you do hit something. And hitting your chest against the seatbelt is a lot nicer than hitting your face against the steering wheel or the windshield or the wall or the pavement, I promise. So first law says that this car's motion is stopped because of the force of this wall, but this man's motion is not stopped because he has not had any forces on him yet. Same idea here with this lady pushing a wheelbarrow that has this kind of rake that she was laying on top of it. She just got all done with her yard work, and now she's pushing her leaves back to the garbage can. And her wheelbarrow hits a rock, and so this rock puts a force on the wheelbarrow, causes it to stop. But the rake doesn't have any forces on it, so it keeps moving to the left until it falls to the ground because of gravity. So an object in motion is going to stay in motion until a force acts on it. So I've been talking about how if you like throw a ball or roll it along the ground or you're traveling in a car or something like that, the first law says that things in motion will stay in motion forever until some sort of force acts on them. So if you're in space, this is true. If you take like a rock or a tennis ball or something up into space and then throw it out into space, that rock or that tennis ball will keep moving in a straight line forever and ever until some other force comes along and acts on it. Maybe it hits an asteroid, maybe it's pulled in by the gravity of some other planet, who knows, but it'll keep moving. So this works really well in space, but this doesn't work exactly like that on Earth for a couple different reasons. So on Earth, if you roll a ball along the ground or you're riding your bike along a flat surface and then you stop pedaling, eventually it rolls to a stop, right? It doesn't keep rolling in forever, or your bike doesn't just keep going forever until you twist the handlebars. Eventually, you'll roll and come to a stop. That's because on Earth, there's almost always some sort of unbalanced force acting on an object. One of the big ones of these is friction. So we'll talk about this a lot more next week, but friction is essentially a force that's caused by objects rubbing against each other. And it causes a force in the opposite direction of how an object's moving. So if you roll like a tennis ball along the ground, the friction between the ball and the ground will put a force that slows down the ball and causes it to eventually stop. If you're driving in your car, right, and you let your foot off of the gas pedal, if you're driving at 60 miles an hour, you're not going to keep going at 60 miles an hour, right? Friction between your wheels and the road will eventually cause your car to slow down. And if you put it in neutral or something, or not in drive, if you're in drive, it'll like automatically go forward at like a couple miles an hour, right? But if you're in neutral, eventually your car will come to a stop. And that's because of friction between your car wheels and the ground. So friction is an unbalanced force that opposes movement, right? It causes things to slow down, or it resists things moving in the direction that they're going. There's also the force that we talked about earlier, the force of gravity. So if you're on Earth or any other planet, there's always going to be gravity acting upon you, right? So if you throw like a baseball straight up into the air, it's not going to keep traveling up in the air at a constant speed forever, right? Eventually, it's going to stop and come back down to the ground. That's because gravity is opposing its movement through the air. Gravity, when something's in the air, gravity is an unbalanced force that'll pull it down to the ground until it comes to rest on something like a table or it's tied up by a string. If it's not, then it will fall to the ground. So there's some different types that we'll get into on a later date, but friction is this unbalanced force. It causes an object in motion to slow down and come to a stop due to the interaction between the two surfaces that are rubbing together. So like you could be sitting still on your bike, in which case your bike is balanced with the ground. So you're stationary, you're at rest, you're not moving. You then apply a force to your pedals and you start going forward. While you're traveling forward, there's friction between your bike tires and the grounds that's pulling you back a little bit. You might not really notice it because wheels and circles are really good at rolling over the ground, and so they only have a little bit of friction. But if you stop pedaling, eventually your bike will slow down and eventually come to a stop, because the friction is the only force that's acting on it at that point, and it is going in the opposite direction of the way that your bike is rolling. So if your bike is rolling to the right, then friction is opposing it and is a force acting to the left. So this is why on Earth, things don't travel at a constant speed forever and ever, because there's almost always some sort of outside force that's acting against it. So if you escape Earth, if you're up in space where there is no friction and there is no gravity, that's when you're able to really see that first law in effect when something is moving, because a thrown object or something like a rocket ship will keep traveling in the same direction at the same speed forever, or until at least it interacts with some other force, whether that's the force of an object in space colliding with it and causing it to go off in another direction, or maybe the force of gravity from another planet that the ship goes by that pulls it down. But if there's no other forces, then that ship is going to keep going the same direction and the same speed. All right, so first law is all about things are going to keep doing what they were doing. If something is sitting still, it's going to keep sitting still. Or if something is moving, it's going to keep moving until some other force comes along, acts on it, and causes it to either speed up or slow down or change direction. All right. So does anybody have any questions about the first law of motion so far? Anything about that Newton's first law that you have questions about? All righty. Edith says no, and I'm not hearing anything from anybody else either. So sounds like you guys are pretty okay with that one so far. Awesome. Thanks, Annalisa. So next law, Newton's second law, can be boiled down to a pretty simple premise. It's a very basic equation that describes how the idea of force and mass and acceleration are related. And it's written simply as F equals ma, meaning that force equals mass times acceleration. So the amount of force that you need to, that you're going to apply to something is equal to how big it is, how much mass it has, and how quickly you're able to get it to speed up or slow down. So acceleration is just a measurement of how quickly things are changing in speed and direction. So if you know how heavy something is, and you know how quickly it speeds up or slows down, you can calculate how much force was exerted on that object. F equals ma. F equals m times a, mass times acceleration. So it's a very simple equation, but it does a great job of illustrating how these three different concepts, these three different ideas are related to each other. Force is equal to mass times acceleration. Excuse me. So there are a couple different ways that we can think about this. The first one is that we can think about how force and acceleration are related. So if you apply more force to a certain object, it will accelerate at a higher rate, right? So here we have this guy pushing this cart that has this little box on it. So this cart has some sort of certain mass. So that means that if we push it with a certain amount of force, its speed is going to go up and it will accelerate over to the right. If we keep the mass the same, so we've got exact same cart, exact same box on it, but our man over here pushes it with more force, that means that it's going to go faster, right? Again, very, very basic idea, but now, thanks to Isaac Newton, we have it put into this particular equation. So the more force that you put into something, if the mass stays the same, then it'll accelerate faster. If two things weigh the same and you push one harder, it'll move faster. So if mass is the same, then if your force goes up, your acceleration will go up as well. We can also look at how force and mass are related. So imagine I give you this wagon and I put a little block on it, and I tell you, I want you to get this block from here to over here in 10 seconds. So in order to get this wagon to accelerate from a stop position and travel that distance in 10 seconds, you're going to need a certain amount of force. If instead of just one block, I put 4 blocks on it and say, all right, I'm going to need you to still get from the start to the finish line in 10 seconds. Your mass has gone up, right? This thing is now a lot heavier. So you're going to need more force in order to get it to move the same amount of acceleration, in order to get it to accelerate the same way over the same distance. So if your mass goes up, then in order to keep that acceleration the same, your force has to go up as well. Again, simple idea, but just put into this kind of equation form, right? If something's heavier, it's going to require more force to push it the same amount as something that is lighter. So if our acceleration is going to be the same, then if the mass goes up, the force is going to need to go up as well. So the nice thing about the F equals ma law is that it provides us a simple way to calculate exactly how much force was placed on an object by just taking 2 basic measurements. So if you can measure the mass of an object and you can measure how quickly it accelerated, you can pretty easily calculate how much force was applied to that object. So like our soccer players here with the soccer ball, if you weigh the soccer ball and you know what its mass is, and you have like one of those little police scanner, like radar guns pointed on it, and somebody comes along and kicks the ball, shoots it across the field, and you measure the acceleration of that ball, then you can easily do the mass of the ball times its acceleration and calculate the exact number of how much force the foot of that person applied to the ball in order to make it move that way. So force is equal to mass times acceleration. So when these guys put an amount of force on the ball that has a certain mass, it'll accelerate in a predictable amount. So again, even if the ball is standing still, this equation also means that if you can measure exactly how much force is going to be applied to the ball, then you can calculate exactly how quickly that ball is going to accelerate and shoot off into the air. So force equals mass times acceleration. If your mass goes up, or if your acceleration goes up, that means that more force has to be applied. All right, so that one was a little bit of a simpler one, but does anybody have any questions about our second law, our force equation, or what exactly it means with mass and acceleration?
No.
All right, awesome. Thanks, Edith.
No.
Cool, thanks, Annalisa. So we have the first law, things will stay still or in motion until acted upon. We have our second law, force equals mass times acceleration. And now the last one, the third law that I'm going to go over with you guys is a little bit trickier, but we'll look at lots of great examples that help to kind of explain what's going on with it. And you may have heard something like the third law before. Newton's third law of motion is the law also known as action-reaction. So when one object exerts a force on a second object, that second object will exert a force back on the first one. So for every force that is exerted from one object to another, that second object will exert a force back on the first one. It's also sometimes called, for every action, there is an equal and opposite reaction. So the force that the second one is exerting is in the opposite direction from the force of the first one. So this is kind of hard to just explain using like words or definitions. So I really like to use a lot of examples to kind of explain what's going on here. And one of my favorite examples is the idea of a rocket ship. So a rocket ship burns fuel. It creates this very contained series of explosions, essentially, in order to shoot the rocket up into the air. So all this fuel is burning and exploding in these engines and these boosters. And those gases, if you've ever seen like clips of rocket ships and stuff, there's all like the gas and the flames and stuff. They all come shooting downward out the bottom of the rocket ship, right? So all this hot gas and stuff is shooting down out of the rocket. But the third law says that the force of that stuff shooting down will exert a force on the rocket ship to go up. So as those gases, as all the stuff that's burning in the boosters is shooting down out the downward side of the rocket moves up. It goes in the opposite direction. Because the third law says that if an object exerts a force in one direction, there'll be an equal force in the opposite direction. So the exhaust, so all of that hot gas and flames and stuff is going backwards out of the rocket ship. So the rocket engine is pushed forward. So for every action, there's an equal and opposite reaction. The backwards flow of the gas and the exhaust pushes the engine and the rocket forward, or in the case of liftoff, it pushes it up. So other things also fly, but not quite using that same exact series of gases. Birds, very famous for their ability to fly through the air and sail on the breeze. The way they do that is through the reaction and action-reaction between their wings and the air. So even though air is super light and super dispersed, it is still an object, and it is still something that can be interacted with. So as birds flap their wings and they push air down with their wings, as they push air down, the air pushes back up on their wings. And that's what gives them lift. That's what gives them the ability to kind of push off of the air and fly through the sky. And you can see it in the little GIF right here. You'll notice that as the bird's wings go down, the body of the bird goes up. And that's because as the wings push down against the air pushes back up against the wings. The wings perform, and the wings exert a force on the air, so the air exerts a force back on the wings. Equal and opposite reaction. Ooh, another good example that, let me make sure I think I got the space here. So imagine that you're like standing on rollerblades or on a skateboard, or you're like me and you're sitting in a rolly chair with wheels. And you go up to a wall or you go up to a table, in my case, and you push against it, right? So for me, I'm gonna grab this table right here, and the force of my push is gonna come towards you guys, towards the camera, right? But when I push on this table, the table is gonna push back on me. And so even though I am exerting a force forwards towards you guys, I get pushed backwards because the table pushed back on me. And since I'm on a wheelie chair on top of a very smooth surface, I moved backwards even though I pushed forwards. So I slid in the opposite direction because I pushed on the table, but the table pushed back on me. And my force on the table was not enough to make the table move, but the table's force on me was. Same thing if I was up against like a wall right over here, right? I'm exerting a force with my arm towards the wall. But when I really push, I go in the opposite direction. And that's because the wall pushes back on me. So I exerted a force against the wall, but when I did that, the wall exerted a force back on me. That is what the third law of motion, the action-reaction law, is all about. When two things collide, when two objects hit each other, they each exert a force on the other object. Even though one object might be stationary and standing still, it's still able to exert a force back on the first one. So kind of similar to the rocket ship example from earlier with a balloon, right? So if you ever had like a balloon, like a party balloon at a kid's birthday party or something, and you know that you have to keep the bottom part of the balloon closed, like the little neck part of the balloon, you have to really squeeze it and keep it closed. So what happens if you let go? The balloon not only does it make a funny sound and go, but it also starts zooming all around the room, right? And that's because the balloon is pushing air out of it through that little hole on the bottom. So the air is rushing downwards and out of the balloon. And this causes the balloon to be forced upwards, or to be forced in whatever opposite direction from the little bottom neck part that it's facing. So these equal and opposite reactions. As the air is pushed out of the balloon, it pushes back up on the balloon and forces it around the room. Kind of similar to the rocket ship we were looking at earlier. Another couple ones that I really like, if you've ever gone to take a step off of a boat, like at the end of like a rafting trip or a canoeing trip, or you're floating on the river or something, and you get to the end where you have to pull into the side and get off, and you go on the very edge of the boat and you step to get off. You move forward because the boat is pushing on you to go forward like you would with a normal step, but you are also pushing back on the boat. So if it's not secured or tied down, the boat is going to zoom backwards and you're probably going to face plant in the water. That's all because of the third law of motion. While the boat is pushing against you to allow you to step off, you push back against the boat and cause it to move backwards. Same thing with somebody swimming through the water, right? You don't swim through the water by forcing your arms forward and just kind of pushing the water in front of you, right? Instead, you reach forward, but then you put your arm in the water and then pull it back. You push the water behind you. So when you're swimming, you're just pushing the water behind you in an organized way. As you push on the water and push it back, the water pushes on you and pushes you forward. So even though the swimmer is pushing the water backwards, the water exerts a force back on the swimmer and pushes them forward. And this is what allows us to swim through the water, is this idea of you push on the water, but it causes the water to push back on you. And it's all thanks to the third law of motion. If one object exerts a force on a second object, the second one will exert a force back on the first. Same thing with like when people are playing baseball and they swing and the bat connects with the ball. The ball obviously has a big force exerted on it, so it goes flying off, but it also makes serious contact with the bat. So the ball, if the bat wasn't sitting in somebody's hand, right, it would go flying because the ball exerted, if it was thrown by like a major league pitcher, that's a lot of force that ball exerted on that bat. But when a batter is holding it and hits the ball with it firmly gripped in their hand, the bat is able to exert force back on the ball and cause it to go shoot off and maybe even get a home run, hopefully. Same thing with if you're like eating breakfast or something, you have your coffee cup in your hand and you decide that your other hand is busy, so you use your coffee to like move an apple around on your table. If the cup pushes on the apple is going to push back on the cup. So all this idea of equal but opposite reaction. So the opposite force is always going in the exact other direction of the initial force, but it is there. All right, so that is the third law of motion. Anytime an object exerts a force on a second object, that second one will exert a force back in the opposite direction on the first one. If I exert a force on this table in front of me, the table will exert a force back on me. All right, so like I said, the first time that we looked at it, it may have been a little bit confusing. But if we go back and look at that initial kind of recap of our laws of motion again, we have our first law. An object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an unbalanced force. Things will stay the way that they are until some other force comes and acts on them. Second law, fairly easy. Force equals mass times acceleration. If you know the mass and you measure its acceleration, you can calculate how much force was applied to it. If there's more mass, you're going to need more force and able to push it the same acceleration. If you want something to go faster, you have to put in more force in order to have it do that. And then finally, our third law, for every action, there's an equal and opposite reaction. For every object that exerts a force on a second object, that second object will exert a force back on the first one. anytime there's any sort of collision or interaction between two objects, they'll always exert forces against each other. All right, so hopefully those three laws of motion make a little bit more sense to you now. Does anybody have any questions about any of these laws of motion or what they mean?
No.
All righty. So since we are still in the first week of class, and we're just kind of getting used to the physics and being back on the Google Classrooms and all that good stuff, I decided to keep it a little bit easy on you guys for the homework for this week. And so for today's assignment, all you have to do is describe a situation that is a good example of the third law of motion. So essentially, in your own words, I want you guys to kind of explain to me this idea of, or give an example of two different objects interacting that shows off that third law of motion. It could be something that we kind of talked a little bit about in class. It could be your own example that you thought up that you see happen in your daily life a lot. Whatever it is, I want you to put in your own words an example of the third law of motion at work. So that is all you have to do for your homework to end off our first week of class. So next week, we'll start to get into a little bit more specifics of how things move. We'll talk about how to measure things like speed and velocity, what exactly is acceleration, and we'll look a little bit more at these forces that we've been talking about, how we can diagram and what the different kinds of forces out there are. But on Monday of next week, so your next assignment will go up on Monday, and it's just a basic syllabus quiz. So I like to do this early in the term because the first couple semesters that I taught here, I was surprised by like how many people in my class didn't know what my name was and didn't know what the class was called. So I created a very basic syllabus quiz that just kind of has some simple questions about this class and how classes at the Excel Center work. As always, you're free to go back and look at that initial set of notes that I went over on Tuesday, but there's also your physics syllabus that's posted right here at the top of the class. So you can use that as well in order to answer the questions on the syllabus quiz on Monday. All right, does anybody have any final questions about any of our laws of motion or any of the assignments coming up for today or for Monday?
No.
No, sir.
Alrighty, guys. Well, as always, if you do ever have any questions about anything, feel free to reach out to me. You can send me a text, you can send me an email, you can leave a comment on the Google Classroom, and I will do my best to get back to you as quickly as I am able. But that pretty much is it for stuff that I want to go over with you guys for this first week here. So I hope you all have a good rest of your Thursday and a good weekend. Make sure to hop back on Monday for that syllabus quiz, and I will see you back for our next set of physics notes on Tuesday.
Okay, thank you. You too, sir.
Thank you. Have a good night.
Thank you, Mr. Stanley. You have a good night.
Yeah, no worries. You too, Annalisa.
Good night. Thank you.
Good night, Nancy. Have a good one.
You too.